discussing a paper that analyzes how models learn. This is really, really interesting. It builds on the concept of circuit formation. So it looks at a model like, let's say, GPT or Grok, and it tries to understand what is actually happening within the model, how knowledge is created, and it builds on the concept of circuit formation, which is the idea that at some point circuits build or relationships between elements in the model that represent knowledge. So knowledge is not stored in data like in a database. I mean, that's the whole concept of modern machine learning method, is that we represent knowledge in terms of what's called parameterized knowledge. So in terms of weights and the connection of weights and the connection of model elements like attention heads and things like that, and not the capital of France is not stored somewhere. This is not an expert system. It is actually learned. So what this paper does is try to analyze this process. I think it's a really, really important paper. The name of the paper, How Do LLMs Acquire New Knowledge? A Knowledge Circuit Perspective on Continual Pre-Training. I think it's out of Singapore. Really, really interesting. So a couple of insights. So the acquisition of knowledge is significantly influenced by existing knowledge. So the more a model knows, the better it learns, particularly similar knowledge. Strength builds on strength. So if you're good at physics, you also become good at chemistry. So very similar to humans, actually. But there's a lot more implications. I'm going to discuss them more in detail. For example, some ideas about actual training methodologies, such as data curriculums. So monitor how the model is learning and tweak your data that you're feeding the model in pre-training to take advantage of the circuit formation while you're training. So kind of a real-time adjustment of what kind of data you feed the model to improve the performance of the training. This is really, really interesting stuff. I think this paper also makes the case for foundation models. I'm going to explain why that's the case. And it also makes the case for something like Weights and Biases, a company that is helping people train better models. So for example, visualizing these knowledge circuits and doing real-time debugging by doing real-time ablation studies or things of that sort. So you kind of you see how circuits are formed, and then you can, for example, ask the model certain things. For example, you can ask the model, how to make bioweapons, and then it explains how that is done, and then you see the circuit that is responsible for that type of knowledge, and then you can tweak the model so it doesn't actually reproduce that kind of knowledge. I mean, maybe this was a bad example, but what I'm saying is you can the mechanistic interpretability and alignment literature is certainly very interested in this part of the model. But here at Orange Capital Partners, we're not so much into trying to generate AI that fits our political views and more effective AI. So in other words, let's say a robotics company wants to train a robot in the most effective way to, let's say, humanoid robot to be able to work in a factory. So what you want to do is also you want to sort of understand its knowledge creation while training and tweak the data that you expose the robot towards more efficient knowledge creation. This is not a podcast. It's April 10, 2025. This is Krim Delco. Before I go into the discussion of this paper, just real quick about the market. For the year, we're down 39.5%. The market is down 9.5%. We're underperforming by 30%. We have unprecedented volatility, which has been triggered by the tariff conversation and the Liberation Day on April 2nd. I don't think that we here at Orange Capital Partners have a lot more insight than what you can see in the news, but there's maybe two things we want to say about this that could be hopefully a little bit value added for listeners. Number one, in terms of the strategy, we are absolutely in favor of restructuring global trade. It has been going into a very, very bad place where The US has been triggering itself into oblivion with large debts and deficits. And at the same time, we have massive trade imbalances that are hollowing out the US middle class, but more importantly, also hollowing out manufacturing prowess of the US, which is not a good thing geopolitically. So in order to restore that, there are certainly ways to do that, but not the way the Trump administration has done it. What we suggest is we suggest a strategic review of industries that the US needs to have, at least at home or with close allies, although we probably don't have a lot of them left. But what I'm trying to say is, like a company that is thinking about vertical integration versus buying, right? Make it myself or buy, the same way a country could think. And I think, therefore, it would be useful for a country to have a conversation. Okay, what is it we actually need, and how can we steer this towards our shores? And I think the ultimate weapon in any of these conversations is not some sort of international relations chess game, but building a strong entrepreneurial class of people who innovate and create solutions for problems, whether it's flexible manufacturing like MachineWorks, a company I just came across from ex-SpaceX engineers that are doing flexible, large-scale adaptive manufacturing, companies like Anduril, of course, Tesla and SpaceX, and there's many others. Yesterday we met Agile Robotics. Companies like that are building real things, difficult things, that are adjusting their supply chains. And as a country, we can help these companies and also create incentives for the supply chains of these critical industries to be at home. So I think that will be more useful than this full blanket trade war type stuff that Trump is doing. Now, we understand the second point we want to make. It's almost certain that this is not the end game. The end game of Trump, as always, is to get something out of this. And you start with 100, and if you get 20, then it's still more than 10. It's kind of that attitude. So if you follow Trump's second term so far, let's say I'm using the Ukraine as an example. They started in January with a splash. J.D. Vance went to Munich, basically told the Europeans that we don't want to support you guys anymore. Then there was the éclat with Zelensky, and then there was this huge backlash, and everybody's yelling and screaming. And fundamentally, the U.S. has withdrawn some help to Ukraine, but not much. They're still helping them without the U.S. intelligence, communication assets, Starlink, and weapons, and anti-missile rockets and things like that, drones, all that stuff. I don't think that the Ukraine would be in the war anymore. So we're still there. So what I'm trying to say is, I think it's going to be probably more like that we have this big splash, and then we'll have deals on behind the curtains, and then eventually these things will calm down. That's the MO of Trump: big ratings, big action, and then we go back to normal kind of things. So that's the way we see it as far as this whole strategy is concerned. Again, we're not here to talk about international relations or anything like that. The purpose of Orange Capital Partners is to generate wealth by investing in fundamentally new concepts and engineering practices. So we're very happy to participate in new American dynamism, in building companies and supply chains that can support this country in potential wars, but more importantly, generate wealth for future generations and make life in this country better for everybody. That's really the purpose of Orange Capital Partners. So having said that, now let's talk about this paper. It's about how knowledge is created. And I think this is really, really important to understand what is actually going on in this type of new models that we have now, the transformer-based models that have unleashed a massive amount of intelligence that we weren't aware of before. We have it now in the language space. We are getting more and more also advanced in the real world space with robotics. We have full self-driving with Tesla, also in that realm. to some extent also Waymo, although I think that's a different approach. The point being that we are really at the cusp of a massive revolution here in terms of intelligence, and it's really useful to understand how that works. And this paper is one of those attempts, and it's a very good paper. We definitely recommend reading it. It's links in the show notes. So what are the key takeaways and practical implications of this paper? So the fundamental takeaway, the methodology of the paper is to look at knowledge circuits. And this is something that I've come across in epistemology for years now, which is, okay, what exactly is intelligence, or what is the difference between humans and animals or trees or whatever? I mean, why are we more intelligent, if you will, than these other living beings? And the answer has always been something along the lines, it's not in some sort of stored knowledge. It's not like we are born with facts. We have a certain connection of neurons and synapses, or if you want, even in our DNA, we have some sort of relationship between DNA and RNA and proteins that allows for a continuous evolution and a learning and adaptation to the environment, something along those lines. And what this means for this particular paper is that they're doing the same thing. Knowledge representation is defined as a knowledge circuit within a large language model, and that is literally the connections between neurons and layers of the model, and how they interact with each other. That's where the knowledge is represented and then also retrieved. So that, I think that's number one, a big takeaway. Number two, what they learn is that knowledge acquisition, so basically if you pre-train a model, you'll get more bang for the buck if you train the model on things that it already has some idea about. Now, I'm not saying you should be training the model on things that it already knows. That would be a waste of time. But for example, if the model is already pretty good at physics, it might be useful to feed it more chemistry data or biology data because it's already good at science. I think this is akin to the old saying, I used to play music when I was a teenager, and people used to say, once you play one instrument, you play all of them. And there's a truth behind that, because once you're good at piano, you also learn guitar and drums pretty fast. So once you build a knowledge circuit, whether it's music or science or math or whatever, it is relatively easier to build on top of these circuits new circuits that are similar, versus if you're good at poetry, it's a little bit difficult to also become good at jiu-jitsu right away. You need more time for that. So that's, what applies to humans, again, applies to these models, which, by the way, as a tangent, is really interesting. Think about it. I mean, isn't this amazing? So other implications of this is that we can visualize these types of circuits during training and sort of see what the model is learning and understand which circuits it's building. We can then try to understand, okay, this type of, let's say, the model's really good at telling me what the capital of countries is. That's in this circuit. So if I want to keep building on that type of knowledge, I want to feed it more that type of data, facts like capitals, mountains, highest mountain of Switzerland, highest mountain of the US, that kind of thing. And then I want to, maybe other type of knowledge like Shakespeare poems. Maybe I shouldn't waste my time now feeding that type of data because it's building this type of knowledge. Now, what this idea, also one of the big takeaways from this paper, is that we have these two levels of knowledge creation. One is the sort of circuit formation. So when circuits are built, so when new knowledge is being created through circuit formation, and then we have optimization, which I think that's the concept of fine-tuning. And it would be good to do in training also to do that. So to start, train on a very vast, diverse data set, create as many circuits as possible, and then at some point start bringing in more detailed data. So in other words, I want to start my pre-training phase maybe with lots of diverse, like I want to feed it some physics, I want to feed it poetry, I want to feed it manuals for coding, manuals for fixing technical stuff, all kinds of different stuff, different languages, everything. And then maybe after 2 or 3 months of pre-training, I want to start becoming more detailed. All right, now in the physics realm, I want to go more specific into particle physics. And there I want to understand better what the fundamental model of particle physics is. That kind of thing. So use data curricula as a sort of like a guideline also towards training. I think also lastly, like I said, you can visualize the circuit formation and therefore we have real-time debugging. Before I end, I just want to sort of lean back and just give a little bit of a reflection on this paper because it made me think it is definitely an endorsement of the foundation model concept. So for example, if you take the robotics realm and you look at what companies like Physical Intelligence are doing, I think this is very much in line with what they're doing, which is you want to start with a broad, general model with lots and lots of general, broad, diverse data and pre-train and generate knowledge or skills, if you will, on a wide variety of topics, and then go fine-tune. So this is very much in line. Now, of course, in the robotics sphere, knowledge is also is not just the cognitive knowledge. So knowing how to screw a screw, or unscrew a screw, or knowing how to cook an egg. There's a semantic understanding. Like I could bullet point how to do that, but then there's also a physical skill how to actually implement it with the hands and all that. Or music, you can write music, but playing is very different. Therefore, there's a different level of knowledge involved in robotics, which is fascinating. I think that's why we're so fascinated with robotics in general. It's just this never-ending cascade of knowledge and interesting ideas that is sort of coming our way. But again, I think fundamentally this paper also justifies the idea of transfer learning, which is the idea that Tesla with FSD has learned a certain skill, and now building on that skill in Optimus will result in quick results very fast, because there is a certain base of knowledge circuits already available that can be fine-tuned towards, let's say, the Optimus use case versus the self-driving use case. I guess to summarize, the conclusion is that you want to start with very diverse and very large amounts of data, large and diverse. So pre-training is a function of compute, eventually a function of energy. And that's where the industry is going, both in the pre-training and the fine-tuning. We believe that there's a statement that Jensen recently said, which is that data is also a function of compute, because you can use, first you can create synthetic data, of course, with compute, but more importantly also in simulation, you want to actually create a lot of diverse scenarios and fail a lot of times, because from the failures you also learn. That's very critical. So that's the summary here. Again, I think it makes the case for foundation models. It makes the case for diverse, large compute data sets deployed with large compute for pre-training, and then the fine-tuning, which is really the, if you will, the test time scaling, or the part where the models extract the knowledge and fine-tune themselves towards actual skill. That, in my opinion, is also it's just a different type of knowledge and can be treated very similarly, just a different type of circuit, if you will, and you have to create those circuits again the same way you create a knowledge circuit. So there's, I guess you can say, there's knowledge circuits and then there's inference circuits, and I think that's that is also a very interesting insight from this paper. Thank you.